So work and energy is what we were talking about pre-spring break. Now we're going to think about something similar. Let's actually start with Newton's second law. So Newton's second law says force causes an acceleration which is proportional to the mass. And by our kinematics definitions, we said that acceleration is really just the derivative of velocity. So that motivates this sort of discussion where instead of applying a force over a distance, we apply a force over a time. And if we integrate to cover the entire time that the force is applied, we should get on the right hand side. So on the left hand side, we're going to be integrating from time 0 to some time. On the right hand side, we'll be integrating from an initial velocity to a final velocity. And when we do that integral, since there's no v dependence except for the dv, we're just going to get m times vf minus v0. Which we might write down as m delta v, but I'm actually going to, instead of factoring out the m, just going to leave it on the inside. So we'll get m v final minus m v initial, and I'll write that down as delta quantity mv. And now we're going to take this bit, this mv, we're going to call that same way we called this quantity up here energy, and we called this quantity work. We're going to name this quantity mv. We're going to call it momentum. And we are going to call this quantity here impulse. Why J and P are used for impulse and momentum, I have no idea. But that does give us a nice symmetry between these two theorems. If we're applying a force over a distance, then the work we do causes a change in energy. If instead we are applying a force for a time, the impulse we do causes a change in momentum. Any questions so far? Because science, that's why J and P? Yeah. I don't think engineers actually use J for impulse because they tend to use little j for the imaginary unit rather than I, like normal people. But physicists, on the other hand, use capital I for moment of inertia, and so that's why we can't use capital I for impulse. All right, so this is our motivation for looking at momentum analysis. Let's get a little more specific. So if impulse is a force applied over a time, And that causes a change in momentum. One of the most useful parts of energy analysis, you might recall, are times where we could say that the change in energy was zero. Right? So we were constantly looking for situations like this because they let us use conservation of energy to connect a system in 2 points in space. It would be really useful if, similarly, we could define a situation where the change in momentum was zero so that we could connect a system between 2 points in time. And in fact, we can do that. So, two conditions. If there are no external forces, then there is no change in momentum. And secondly, if the time involved is really small, then the change in momentum is approximately zero. So we have to be careful. So wanting the external forces to be zero just means that we have to be careful in how we define our system if we want to use conservation of momentum. For the second case, we can use the momentum to analyze situations that are very fast, even if, strictly speaking, there are some external forces. So what are some situations we'd like to analyze that are, in fact, very fast? Anyone have an idea? Bullets, yep, this is true. Comets? Are comets fast? Planes? Planes are fast, but flights are not fast. Like, flights can last for hours. Light, sure. What I'm thinking of here for times that are very small, thinking about collisions. So collisions happen really fast, fraction of a second. And so that becomes a natural thing to want to analyze with momentum analysis. Let's take a look at a collision. So say we have two objects. And they are going to have a head-on collision. The collision is fast, but how should we draw our system so that during the collision there are no external forces? Alright, so during the collision, if object 1 hits object 2, what are the forces on object 1? I will call on people. I know it's the first day back, but we still gotta get our brains in gear. So object 1 might have gravity, for sure. If it's on a surface, it could have normal force, for sure. Maybe there's some friction. But more importantly, during the collision, what is the largest force on object 1? Yeah, that's right. The largest force on object 1 is going to be contact force from object 2. So can we uh, can we define our system in such a way that the force from 2 on 1 is not an external force but an internal force? And it turns out, yeah, we can definitely do that. If instead of just analyzing object 1, we analyze the combination of 1 and 2 together. If 1 and 2 combined are our system, then the force of 2 on 1 and the force of 1 and 2 on 2 by Newton's third law are equal and opposite. So they cancel out. And so that contact force is not an external force, and in fact, contact force cancels. So the net contact force is 0. So now, if we define our system as both together, right? Everything inside that orange block. Now, there really are no external forces during the collision, except maybe there's friction during during the collision. But if there is friction during the collision, it is relatively small. And we still have to fall back on that time is very, very small. So even if there is some friction during the, I don't know, quarter of a second during which the actual collision occurs, the amount of impulse that friction can provide during a quarter of a second is pretty small. Any questions on this so far? Jaden, what do you mean when you say the net forces of both? And the forces of each block make up V1 and V2. Finding the sum of the two makes the system. Yeah, okay, so you were on the track of what we were going after. That if you sum up the contact forces, they cancel out. So with this in mind, let's take another look at our bullet block. So if we apply a force, if we shoot a bullet into it here, so we have two situations. And I'm not a very good artist, so I'm just going to draw a bullet as a smaller box. And we're going to say that the bullet has a mass m1 and it's got a velocity, initial velocity of v1, in, um, initial, we'll use I, v1 initial, and the larger block has a mass of m2, and its initial velocity is 0. So our system is the bullet and the block together. And we use momentum to connect a system for between 2 points in time. So for the point in time A will be just a split second before the collision. And then for B, time B will be right after the bullet has stopped moving inside the block. And so our delta T is just however much time it takes a speeding bullet to penetrate whatever distance into this wooden block. So it's a really short amount of time. Now let's see what momentum analysis has to say about it. So we're going to go ahead and say that momentum is conserved. So there's no change in momentum, which means that the momentum at A is equal to the momentum at B. And here, when we were doing energy analysis, A and B would have been, point A and point B, but now we're looking at time A and time B. At time A, just before the collision, the only thing that had momentum was the bullet. So we have M1 V1 initial. At time B, both the block and the bullet are moving, and they have the same velocity. So we'll say they have some final velocity and their total mass. So that just means that the final velocity, and by final we mean velocity directly after the collision, is going to be equal to m1 v1 divided by the sum of the masses. Notice that nowhere in this expression does it matter where the bullet enters the block. Right? So the position where the bullet hits the block, it just doesn't matter in this analysis. So if we are looking at the bullet and block in terms of momentum, then we can say, oh, well yeah, both blocks are going to fly to the same height because both blocks will have the same velocity just after the collision, which means they have the same translational kinetic energy just after the collision, which means they will have the same gravitational potential energy at the top of the arc. Is everyone with me here? Sadly, yes. Don't worry, I'm not actually going to take a point off your next quiz. Although, Jaden, I am actually going to add one for you. So with this in mind, let's finish watching this video.